Hi everyone, this is 2.4 Rates of Change in Tangent Lines for Calculus AB. Okay, so first thing is we need to distinguish between finding an average rate of change and what they call an instantaneous rate of change. So first off, we'll talk about average rate of change. So if you're asked for the average rate of change of a function, they have to give you a time interval that they're referring to. And by definition, the average rate of change is basically going to be the slope between those 2 points, the 2 endpoints on the interval that they're giving us. So if I have x1 and x2, then basically the slope I calculate with my usual slope formula, delta y over delta x, or this way, however you want to think of it. But you're calculating your slope between the 2 endpoints. Remember, when you're thinking of it graphically, the x-axis is always your time frame, and then the y-axis can be whatever it is that you're looking at. Okay. So a quick example here, it says find the average rate of change of the function over the interval. So the function is given 2 plus cosine t. The interval 0 to t. So again, the interval 0 to t is going to be, oh, you know what? I said that wrong. Hold up. Okay, sorry, I had a little typo in there. So anyway, I have f of t equals 2 plus cosine t on the interval 0 to pi. Okay, so the question is find the average rate of change. So since I was given the interval 0 to pi, I would plug in 0 for cosine, plug it in for t, and then plug in pi for t, and that's going to give me this part here, the f of pi minus f of 0. And then divide that by, basically you subtract, so pi minus 0. Here it is down at the bottom. And then f of pi, you have to kind of remember your function notation. So f of pi would be 2 plus cosine pi. F of 0 would be 2 plus cosine 0. Subtract all over pi minus 0 is pi. And when I simplify this down, I get negative 2 over pi. That is going to be the average rate of change of my function on the time interval 0 to pi. Okay, so I said before we wanted to make sure we could tell the difference between average rate of change and instantaneous rate of change. So again, with the average rate of change, we said that you have to have a time interval that they're looking at, and then you find basically the slope between the 2 endpoints. Well, when you're doing instantaneous rate of change, as the name implies, you don't have 2 points. You don't have a time interval that you're looking at. You have one single time. You know, what's the rate of change when t is 3? Something like that. Okay, so to calculate it though, we still really actually need to calculate the slope at that particular point. But we haven't learned how to calculate slope at a single point. We only know how to calculate slope between 2 points. So what do? Well, we basically say that we have 2 points. And we pick the 2 points to be very close together, so that basically that line that's going between the 2 endpoints looks like it's almost tangent to the graph. Okay. In fact, if we let the distance between those 2 points shrink down to nothing, then the 2 points actually will end up getting forced on top of each other, and it will look like a tangent line, right? I mean, the slope of the line that connects the 2 endpoints will look like its tangent instead of just connecting 2 endpoints. Okay, so that distance that our 2 points are apart from each other, we call h, and we're going to take the limit as that h value shrinks down to nothing. So when you're looking at f of x plus h, you basically plug in x plus h to your function, and then subtract, and f of x is just your function itself, and you put that whole thing over h. This is what we call the difference quotient. You'll actually see this again in the next section. They'll do it more formally right before introducing derivatives. But for now, it's just trying to think of it in terms of instantaneous rate of change, needing 2 points to calculate the slope between, and picking the 2 points really close together by letting h be 0. So here's an example. It says, what is the rate of change of the volume of a sphere with respect to the radius when the radius is 2 inches? And again, the question is asking us for an instantaneous rate of change, not an average, because they've given us an exact time when the radius is 2 inches, right? They didn't say over the time interval from 1 to 3. They said, oh, when the radius is exactly 2 inches. Okay, so first off, I'm just reminding us, volume of a sphere, 4/3 pi r cubed. And again, when I'm thinking about it, it's the average rate of change of volume. So I do need the volume equation. So if I plug in 2 plus h to the volume equation, and then I plug in 2, and simplify it all down, I am going to get my answer eventually. But as I'm doing the algebra, since it's a little bit long and tedious, I might point out to you just a couple shortcuts. So when I distribute the 4/3 pi in here, let's see, first I cubed this out and multiplied it all out. Eventually I'm going to distribute that 4 pi over 3 in there. When I subtract 32 over 3 pi, we should get those basically canceling out. Here, the very first time I distribute. So 8 times 4, 32 over 3 pi, right there. So when you're doing these problems, the v of 2, whatever it comes out here that you're plugging into your difference quotient, that part should all be canceling out with things earlier in the problem. And then whatever you have left inside, all of those terms should have an h as well in them that can be factored out in front and then eventually canceled with the h on the bottom of your equation. Okay. I put off on the side, those of you learned, some of you learned derivatives last year most likely in pre-calc at the end of the year. So if you wanted to do this problem with calculus, you would take the derivative of v. So 3 comes down, that's 4 pi r, subtract 1 from the exponent, and plug in 2, and you get the same thing. So this is going to be our shortcut when we get to chapter 3 on how to take derivatives quickly. You know, the first part of chapter 3, they're going to have you take derivatives the long way with this difference quotient definition. Okay, last concept here, slope of the curve. So here in black is my curve, okay? And let's say I'm trying to figure out what the slope is at my point P. So the idea here, even from the previous slide, is that you can't find the slope at a particular point. You always have to have 2 points to find the slope between. So I have this other point Q, and I would find the slope of the line PQ. But if I'm really trying to find out what the slope of the curve is at point P, I would want the tangent line at point P, not the secant line at point P. So the tangent line, well, basically as Q gets closer and closer to P, let's say this point over here now is Q. Well, that secant line going through the points P and Q actually is getting closer to be the tangent line at point P. The tangent line, remember, never crosses through the graph. It's just touching it at that one point. So the secant line starts looking more like the tangent line if the Q value is getting closer and closer to P. Okay, so what I put up here is secant line cuts through the curve in 2 points and has a slope given by, and this is really nothing more than your standard slope formula, change in y over change in x. And the tangent line touches the curve at 1 point and has this as its formula. Okay, so for the tangent line again, our point P is x1, y1, and our point Q would be like x2, y2, or you could say it's x plus h, because it's a h away in the horizontal direction. So f of x plus h minus f of x all over h. Okay, I put here at the bottom the main concept is that as Q gets closer to P, our red secant line becomes more and more like the blue tangent line, and that the blue tangent line will eventually be tangent to the curve, and the line that's tangent to the curve at point P is the definition of the slope of the curve at point P. Okay, I put 3 practice problems on. So the way the practice problems work is basically you're going to write them down and you're going to try them now. They're all on topics that we covered just a minute ago. And then after you have them all done, put them in a safe place because tomorrow in class I'll have you guys checking your work and seeing if you have questions on it. Okay, thanks so much. That's it for tonight.